Hello everybody and welcome to a quick introduction to buffer overflow. For the purpose of this demonstration, I have set up a VirtualBox host-only adapter with 192.168.20.1/24 configuration. We got our Kali Linux attack machine, and we got our victim machine running Windows XP Service Pack 3 with war FTPD 1.65. The software suffers from a buffer overflow vulnerability whenever we try to pass in a very large string pertaining to the username. So without any further ado, let's start. I have prepared, as usual, a couple of scripts which are going to aid us in our development. I shall try to explain them as we go along. So first and foremost, we got our machine right here. This is the vulnerable software, war FTPD. We start the software, we put it online so it's accessible. We see that the IP number and port are as default ones, 21 for FTP, for the file transfer protocol, and this is the IP address of the Windows machine. We also start Immunity Debugger, and we attach the program. By attaching the program, we could catch every single call within the registers. We are usually worried about controlling the EIP. This is what's usually aimed for whenever we talk about exploit development. Now, do remember this is a very basic introduction, so we shall not delve into advanced topics, but nonetheless, this should give you a very good introduction to buffer overflow. Okay, so I got my Kali Linux machine over here, and with Kali Linux, within this part right here, I have prepared a script. It's called first.py.python. Okay, so what am I doing here? I'm creating a buffer with 1,000 chars, 1,000 characters, 1,000 A's, and then I'm creating a socket right here. And then I'm connecting on that socket, of course, on that IP address on port 21. And as the username, I'm sending the buffer. And then we're going to try to see what the response is. So let's execute the script as Python first.py. Let's go to the Windows machine and see what happens. As you could see right here at the bottom, we have an access violation when trying to execute 41, 41, 41, 41. Why? Because the EIP is trying to execute instructions which reside at this memory address, which of course it's our A. We managed to overfill the EIP with A's. So now the natural question presents itself. How many A's are necessary in order to fill my buffer? So of course we could try with 500. If that works, then we try with 250. If that works, we go between halves, the traditional algorithm. However, in this case, we have a better tool at our disposal within Metasploit. It's called pattern create. It creates a unique pattern. And let's see, we go back to Kali Linux, and it's located right here within the Metasploit framework within the exploitation tools. And let's execute pattern create. Pattern create for 1,000 characters, nothing more. Now, I have already done this before. So I created another file with this very same string that you see right here. I put in that file. And the file is called second.py. And as you could see, the string, it's exactly the same. So what did I do over here? Instead of having the 1,000 A's in the buffer, I just placed this long string. So now we are going to execute second.py. First, we need to restart the FTP server because it crashed right now. We need to restart it. Oh, before we restart it, it's very important for you to see something, especially to the people who are new to exploit development. Let's just start it within the debugger, and let's see what happens if we crash it with an A or with a B or whatever. Let's see, if we run again, if we were to run b.py or second.py, let's run it and see what happens. No, let's run it first with the first script, so you see what I'm talking about. So in this case, the program just crashed. So now you have a confirmation because I realized I started the program directly in the debugger. So you might have not been knowing what I'm talking about, but that was a confirmation of the fact that the program crashes, okay? So now let's start the debugger again. Let me attach the running server, which is somewhere around here. There you go. Let's attach it. Now don't forget, by default, when it attaches, it's paused, so we have to run it. Now we are running it. And now let's find out if we execute the second program, so Python second.py, and see what happens. Go back to the program. So now again it crashed, but our EIP this time it's overloaded with a unique string 32714131. So what we do, we need to find the offset at where this unique string is located, and for that we got another wonderful tool within Metasploit called pattern offset. So instead of that, we have pattern offset, and we need to pass 3271. Forgot what the name of the error was. 3271 4131. 4131. And this is going to give us the exact location where our buffer has crashed. Okay, it's telling us it crashed at 485. Okay, so what we need to do at this point in time, since it crashed over there, we need to create another Python file. We are going to call this second of third. So cat second.py, and let's pipe everything to third.py. And now let's open third.py. And now here's what we are going to do. Instead of this buffer right here, instead of the wrong buffer, let me just comment this right here. I'm not in the mood to erase the whole thing. Let me create another variable called buff. And inside buff, what am I going to put? I'm going to put 485 A's just to test our theory, whether this is right or not. And then I'm going to fill up the remaining of the 1,000 characters with B's, which of course we could subtract 485 from 1,000, or you could just do this right here if you're lazy and let Python do the work for you. And of course, just to be safe right here, you have to send a variable buff, because we just changed the name of the variable. I was not in the mood to change the whole thing. Okay, so let's see whether our theory is right. We have to run third.py, but before we do that, let's restart our server. And let's run it at the same time. Okay, let's put it online. And now let's see whether our theory is right or not. So we run again Python third.py. And okay, it seems we got a response. Let's see what happened. So it seems that our theory was right indeed. We had 485 A's, which, if you pay attention right here to the stack, are filling everything up to the EIP, and our EIP is filled up with a bunch of B's with 42, 42, 42, 42. So, okay, if this is the case, then actually the question is, okay, what do we do next? We need to be able to somehow modify the EIP directly in order to run shellcode, but unfortunately that's not possible. We cannot modify the EIP directly. So we have to put our code on the stack with the extended stack pointer, with the ESP. So since we cannot modify the EIP directly, we have to be a bit cleverer. Of course, I'm just going to make a parenthesis. We could call the code with the address of the ESP, but that's not a universal exploit. That only works on this operating system. So we want our exploit to be as general as possible. So what we are going to do, we are going to look for a static DLL, and in Windows XP, they're pretty much static. Everything after Windows Vista and later on involves some advanced techniques, but nonetheless, that's in another course. So now here's what we do. We take a look at the executable modules. And for instance, everybody should know that every time we have a graphical user interface, user32.dll automatically loads. So let's double click on that. And now let's look for an instruction for all commands. And now let's look for jump exp. I would like to jump to exp. All right. So I have already prepared this right here, and I was jumping to that to F7. So I chose this instruction right here, 7E4558F7. Okay. which you could view it right here in code. It's a jump EXP instruction. So now what's our aim? Instead of having 4 Bs inside the EIP, let's put that instruction in there. Take into account little endian notation, and you're going to know that the string reverses normally. So let's restart the server again because it crashed. It's restarted. Now let's start it again. Let me set a breakpoint at that jump instruction, so we convince ourselves that our theory is right. We have 7045 5A F7. It seems that our breakpoint was set. To confirm that, let's view the breakpoints. So we got a breakpoint right there. So now we need to modify our Python script in order to send that code instead of the B's right there. So let's just modify this right here. That doesn't really matter. And so instead of the B's, we have to send that code backwards. So escape my chars, and then we have X. And then do remember it's little endian, so it's F75A. F7 5A 4570. Okay, it seems it's about right. And now let's overfill the whole thing again with B's. And this time it's 489 chars out of the 1000. So we are left, if my arithmetic is correct, with 611. Of course, we could leave Python do the math for us. Let's go Control X, and now let's run third.py. So now if our hypothesis is correct, when we run third.py, we should hit our breakpoint. Let's see whether that happened in Windows. So it seems that it did happen. We hit our breakpoint at the jump EXP instruction. As you could see, the EIP is filled up with 7045 5AF7. And it is indeed located at users 32, that memory address. And now a very interesting thing. Let's take a look at the ESP extended stack pointer. Let's follow it in stack. And let's take a peek at it right here. So it seems that the ESP starts at this address, 00AFFD58. So what this tells us is that we need to place our exploit code 4 bytes away, 1 word away from our jump EXP instruction. So we need to leave the 4 B's right here. So let's restart this. Let's go back in Python. We restarted this. Let's run it. Let's clear this right here. Okay. So now modify the script again. What do we need? We need to leave 4 B's away, or whatever we want. And now from here on comes our code. And as a confirmation, of course, we could execute it with the C's or whatnot. So we check our hypothesis. Let's do it extremely fast. So since we had before 611, now we have 607. I think 493, yes, 607, if my arithmetic is correct. And let me just execute it very fast so you see we are right indeed. So here's what happened. Yes, the ESP contains the C's. So we were right because we filled that with C's. Our EIP contains the breakpoint, so everything works as expected so far. And then the point next to the EIP, what interjects between the EIP and the ESP are the 4 B's, but somehow we need that code in there in order not to mess up our exploit. Now, we need to generate our exploit code. We are going to do that with the Metasploit. But before we do that, let's have a bit of a conversation about bad chars. What could go wrong when writing an exploit? So a couple of things could go wrong. You could have bad chars. What are bad chars? They're characters which could terminate my string, where the string could be faulty because of the bad chars. So I wrote a small C program in here. and I think I also have it here. Let me just see. Yes, I do have it here, and let me get it. The program bad.c, so you see it. So basically, I'm looping from 0 to 255 and print every char in hex, so nothing really special about it. If I already saved it, I got it in bad.txt. So now, in order to test my theory about how this works, we need to actually append all these chars to our Python script. So let's just do that. Let me read bad.txt. So let me get it bad.txt, and let me just append this right here to our Python script. Let's create another Python script from our last one from third. So cat third.py to fourth, or to bad.py. So this is how we check for bad chars. And now nano or get it bad.py. Okay, so let me just, this is commented out already. So instead of the 607 C's right here, just gonna add another variable called bad, and this variable I'm going to define right here is going to contain all those hex chars. I don't know if this is allowed in Python or not. I guess it is. The syntax I'm referring to this end of the lines right here, but well, let's see. First, let's restart the server because it's in a violation right now. So we restart the server, and now I'm going here. I'm online with the server, and let's see what happens if we run bad.py. So Python bad.py, hopefully it runs. It did run. So let's see what took place over here. So our server, it seems that it crashed. Now, why did it crash? It seems it encountered a 0. Let's find the data in stack. So we followed the dump, and as you could see right here, we have 01, we have 02, 03, 04, all the way to 09. But when it reaches 0A, because which is the following character after the 09, 0A, it crashes, okay? So since it crashes, we already know that 0A, it's a bad character. Now I have already done this right here, and I found out these are the bad characters. So without any further ado, I should go straight to the generation of the payload, okay? Let me just restart this right here, but it's a very basic subject on how to find bad chars. It's, I mean, that's the procedure, as I have explained it before. So now what we need is shellcode. But right before we go into our shellcode, we have seen that our code requires some space to run, some breathing room, so to speak. So we are going to add something to our shellcode to our third Python file, which is called a nop sled. A nop sled, it's an instruction that tells the processor, you know what, don't do anything, just slide over. And let me add some code. So let's add our nop sled. The nop sled has this code, x90. And let's add the nop sled by multiplying, I don't know, give me 10 nop sleds so far. And then from 607, I have 597. I have whatever chars left over here. I need to put my shellcode, which we need to generate. We did not generate the shellcode yet, but we are going to in a couple of seconds, okay? So now let's go to our file, and this is the command which we use to generate the code in the format of Python. We did agree that we could use 607 bytes left, and I'm excluding the bad characters. So let's execute the command. Let me just click on that. Matter of fact, third.gi. Okay, so let me execute this and see what happens. Wonderful. So we got our shell code. We're asking for a bind shell. We're using Shikataganai as our encoder, which is probably the best encoder within Metasploit. So let me copy this right here. Let me make another file, shellcode file. So get it shell.txt. Let me paste it over. Let's find and replace buff with shell. Good. Let's save it. Now let's copy and paste the shellcode to our file. So our last file was stir.py. Let's get it, stir.py. And we need the shellcode. I think I called it shell, not shellcode in this case. Doesn't really matter. Let's see what's up over here. So we got the shell. So let's see if this is going to run or not. It should. Unless I made a mistake, I don't think so, but we're about to see in a couple of seconds whether that's the case or not. Let's restart our server. Where is it? Windows. Okay, it's online. Now let's see what happens. Now this time it shouldn't crash if we are right about our exploit. Because what's the point of crashing the server and then you cannot execute anything? So Python stir.py. See whether we have any surprise or not. No, it seems it's still running. And since it seems it's still running, let's use netcat on that IP address of the server on 20.101. By default, I use the port given by Metasploit 444. In real life examples, I wouldn't. As you could see, we have access, we develop remote access to the desktop, and we could run Windows commands on the box. Now, a word right before I finish this demonstration. A lot of people might ask, well, why have you chosen Windows XP? The reason for which I have chosen Windows XP is because, first of all, it's a very basic introduction, and other operating systems utilize something called DEP, Data Execution Protection, and ASLR, Address Space Layout Randomization, where the DLLs are not static. Every time you restart your computer, they charge in a different memory space. So does it mean that you cannot write exploits? No, absolutely not. You could write beautiful exploits, except you have to use techniques such as ROP, return-oriented programming. But those, once again, are advanced techniques, and I teach those in a paid course and in consultations. Well, this should be all for today. I hope you enjoyed the basic buffer overflow demonstration. Thank you very much.